One thing I want to emphasize is here you can see there is no negative sign, right? Same as in GV, right? It is because there is no phase shift here, right? Same phase V signal, part of this is becoming VI, and part of this VI is becoming VE, VBE, and the other part, the remaining part is V out, right? So this is V out as far as input stage to the output of the stage gain is concerned, right? So common collector amplifier has no phase shift between input to output. This one already given to you. Now just explore the common collector amplifier circuits as shown in your book. They have represented a circuit of this kind, right? Here we can say it is a common collector circuit because we have input at the base and output at the collector, right? And if we think about the AC operation, input AC from base, output AC from emitter, and collector is this DC source will be appearing as a ground. So it means base to ground or base to collector is input, emitter to collector is output. So collector is common, right? And it is called emitter-follower circuit because output is to be followed at the emitter as soon as you have an input at the base. So this is its equivalent circuit, right? We can replace this transistor with its T model because we have something at the emitter. So T model with R0, RE, and this. Here they used alpha IE. IE here we used VBE and GMVBE. It's equivalent. We had already discussed it many times. So here they have a current source. We had RE, right? So if they have a current source, when we are on DC current source, right? When we want to have its AC equivalent circuit, then this AC DC current source will be appearing as open circuited. It means there is nothing here, right? But in our circuit of common collector amplifier, we had a RE, so we placed RE here. So it's not much difference depending on our configuration. So we can also simplify this because this R0 is here to ground and this RL is from here to ground. So we can put this R0 here to show a ground here. So these becomes parallel, right? Similar to our circuit. And just one thing is not present here, which is RE because they haven't used RE, right? So if we had RE, we would have to take parallel combination of these three resistances, right? So now we can take this one for further analysis, right? So what we did, we said that part of this signal is becoming V in, and that V in is same for RB and its parallel resistance. What is what? What was that? It was RIB. RIB is 1 plus beta time RE plus this one, parallel of these things, right? And then part of that VI would be RE and remaining part would be R0, right? So to have a simple analysis, they said that because this circuit is no more providing any functionality or computationally critical to find V out, right? Of course, this is a part of the transistor, right? Equivalent circuit. Transistor is working because of this thing, right? But as far as V signal to V out is concerned, it is not doing anything. So it means we can say that instead of using these resistances by having 1 plus beta and reflecting here, we can have an equivalent circuit of this as if we have these resistances multiplied by 1 plus beta already available at the base side, right? This thing. So now it is a simple resistor network. You have to find V out here out of this V signal, right? So it would be the same as we did, right? So V signal part of this is VI. VI would be distributed amongst this and parallel combination of these things, right? So they actually what I said here, we use that version. They actually said that how to reduce this circuit further. So they said that let's Thevenized here. So they Thevenized here and a resistor and a voltage source, right? This one. And then they found that this resistor and this resistor and this and these parallel combinations would be the remaining network, and they drive these formula. We can prove that this formula is similar or same as we found, right, by putting all the values of Rn and other things, right? But we don't need to do that, right? So it's the same. Or instead of bringing this circuit to the base side by multiplying by 1 plus beta, we can bring this circuit here by dividing by 1 plus beta, right? So it's the same. We can bring this circuit to the emitter side by dividing it 1 plus beta and then have only resistor network to find voltage output out of this V signal, right? So again, they Thevenized here, but what we can do, we can have a V input here. That V input would be same here and here, and then part of that V in would be here, and part of that another part would be V out, right? And to find V in here, you have to find R in here, and R in will be RB divided by beta plus 1 parallel with series combination of, actually what we did, parallel combination of these in series with this. The whole network is parallel with this, right? And this is Rn. We did it, right? I am just repeating to let you know or let you remember. So we had finished the discrete BJT amplifier topic. Let's have a comparison between common base, common emitter, and common collector amplifier configuration. It is an amplifier, then VBE need to be nearly zero point 0.7, right? So how about common base? Common base means base would be common, then you have collector is available, output would be at the collector, then emitter have to play the role of input port, right? Common base circuit has input to output phase relation 0, no phase shift, right? We already did it. Voltage gain is very high, right? Current gain is very low, only alpha, right? Because IE would be disturbing by this signal and IC is your collector current, right? And there is a alpha relation between IE and IC. It means this is very low current gain. Then because current gain is very low, even voltage gain is very high, but power gain is low, right? The disadvantage, the significant disadvantage of this circuit, this amplifier is it has low input resistance and high output resistance. It is just the reverse of what we actually want from our amplifier stage. Our amplifier stage should be having a high input impedance so that it can take more power from the signal, right? V signal, and has low output resistance so that it can deliver more power to the load instead of taking on its R naught, right? So because it has very low input resistance, so this kind of circuit only RE, right? These kind of amplifier, common base amplifier, has very limited used, in which the R signal is very low, right? For example, in your lab you used coaxial cable for the oscilloscope, right? And the oscilloscope cable has 75 ohm or something as the resistance, right? So if you want to amplify that signal, you can use the common base amplifier locally, but for other signals it is not suitable. Then comes the common emitter amplifier, right? So common emitter amplifier with emitter resistance or without emitter resistance. So when we said only common emitter amplifier, it means we have even if we have RE, but it would be bypassed, right? So it means no RE in the AC equivalent circuit. So in fact, common emitter amplifier has 180-degree out of phase relation between output and input, right? Output is 180-degree out of phase as compared to the input. Its voltage gain is medium, not very high, not very low, but medium. Its current gain is medium because both are medium. It means its power gain is high, right? Its input resistance is not very high, but not very low. It's medium. Its output resistance also is not very low, which is actually usually we had a demand. We have demand, but medium. We have a common emitter amplifier with emitter resistance to stabilize beta, right? You remember that. But that actually reduce the gain, right? We already know that. So it is still remains in the medium range and high, medium, medium, right? So although we don't have a good input and output, the ideal relation, but still not worse relation as common base have has, right? So common emitter has, that's why common emitter is most useful. High, medium current gain and output current gain and current gain, right? And input and output impedance as medium. Now about the collector, common collectors circuit, we already discussed. Here, zero phase shift, right? No phase shift. Voltage gain is low as 0.99, nearly 1, right? We just saw. Current gain is very high. This is very good. 1 plus beta time of the resistance, right? It has power gain medium, good, because voltage gain is low. Even current gain high can bring the power gain to medium range. Input resistance is very high, very good thing. Output resistance is very low, the very good thing. It means in this table, if we want to compare the impedances, then this amplifier is the best, right? But voltage gain is very low, but current gain is very high, right? So what is the conclusion? The conclusion is, for example, if you are required by a user to design an amplifier for a mic to drive a speaker, right? It does not mean you have to design only one amplifier stage of this kind or this kind or this kind. Your solution can be a combination of more than one of any of these things. For example, if somebody asks me to design a uh, an amplifier to drive a load speaker, right? For let's say 10 gain, voltage gain, right? And current gain is also need to be in the medium range, even if not high, not low, then at least at the medium range. So I would prefer to use this transistor at the input so that it can take the input signal as high as possible because it has a very high input impedance, sorry, right? It will not do anything to the gain, it will deliver the same signal, but it will actually take the signal from the V signal, right? And then I would be having any of these amplifier to have a gain, voltage gain, right? And its output impedance very low. Even this common emitter has medium input impedance, but it can take the signal from it, right? And then I can have another of this one to have a reverse phase shift again, and then common collector to have a better output impedance to deliver my signal at the load, which is the speaker. Okay, so this is all about BJT amplifier configuration. We will discuss soon, inshallah, the PNP transistor, right? I will go through it very quickly because it would be the same. Just need an introduction and how you can use the models for common for PNP transistor, the pi model and P model. And then I will show you only the common emitter amplifier with PNP, right? And then you have to do other configuration, all these other configuration yourself. Okay, thank you very much.